Model selection in HMM. Just like any model, the complexity of an HMM should be tuned so as to balance its complexity with the size and the properties of the data at hand. One possibility is to tune the topology of the HMM. In a fully connected ergodic HMM, there is a transition from a state to any other state, which makes a full n by n matrix. In some applications, only certain transitions are allowed, with the disallowed transitions having their aij equals to 0 when there are fewer possible next states. N prime less than n, the complexity of forward-backward passes and the Viterbi procedure is big O of n times n prime times t instead of big O of n squared times t. For example, in a speech recognition, left-to-right HMMs are used, which have their states ordered in time so that as time increases, the state index increases or stays the same. Such a constraint allows modeling sequences whose properties change over time, as in speech, and when we get to a state, we know approximately the states preceding it. There is the property that we never move to a state with a smaller index, namely aij equals to 0 for all those j less than I. Large changes in state indexes are not allowed either, namely aij equals to 0 for j greater than I plus tau. The example of the left-to-right HMM given in figure 15.5 with tau equals to 2 has the state transition matrix as follows. It's a 4 by 4. Okay, this is a matrix A and it's a 4 by 4. The first line is A11, A12, A13, and 0. The second line is 0. The row 2 is 0, A22, A23, A24. And the third row is 0, 0, A33, A34. The fourth row is 0, 0, 0, and A44. Another factor that determines the complexity of an HMM is the number of states n. Because the states are hidden, their number is not known and should be chosen before training. This is determined using prior information and can be fine-tuned by cross-validation, namely by checking the likelihood of validation sequences. When used for classification, we have a set of HMMs, each one modeling the sequences belonging to one class. For example, in a spoken word recognition, examples of each word train a separate model, lambda I, given a new word utterance O to classify. All of the separate word models are evaluated to calculate P of O conditioning on lambda I. We then use Bayes' rules to get the posterior probabilities. That is, P of lambda I conditional O is equals to the probability of O conditional lambda I times the probability of lambda I divided by the sigma summing for all j of the probability of O conditional lambda j times the probability of lambda j, where the probability of lambda I is the primary probability of a word I. The utterance is assigned to the word having the highest posterior. This is the likelihood-based approach. There is also work on a discriminative HMM trained directly to maximize the posterior probabilities. When there are several pronunciations of the same word, these are defined as parallel paths in the HMM for the word. In the case of a continuous input like speech, the difficult task is that of segmenting the signal into small discrete observations. Typically, phones are used that are taken as the primitive parts and combining them. Longer sequences, for example words, are formed. Each phone is recognized in a parallel by the vector quantizer. Then the HMM is used to combine them serially. If the speech primitives are simple, then the HMM becomes complex, and vice versa. In a connected speech recognition where the words are not uttered one by one with a clear pauses between them, there is a hierarchy of HMMs. At several levels, one combines phones to recognize words. Another combines words to recognize sentences by building a language model and so forth. Hybrid neural network HMM models were also used for speech recognition. This is proposed by Morgan and Borland in 1995. In such a model, a multilayer perceptron in Chapter 11 is used to capture temporarily local but possibly complex and nonlinear primitives, for example, phones, while the HMM is used to learn the temporal structure. The neural network acts as a preprocessor and translates the raw observations in a time window to a form that is easier to model than the output of a vector quantizer. An HMM can be visualized as a graphical model, and evaluation in an HMM is a special case of the belief propagation algorithm, as we will see in chapter 16 later on. The reason that we devote a special chapter is the widespread successful use of this particular model, especially in automatic speech recognition. When we discuss graphical models in detail, we will see how the basic HMM architecture can be extended, for example, by having multiple sequences or by introducing hidden latent variables that can simplify the model. Notes: the HMM is a mature technology, and there are HMM-based commercial speech recognition systems in actual use. In section 11.12, we discussed how to train multi-layer perceptrons for recognizing sequences. HMMs have the advantage over time-delay neural networks in that no time window needs to be defined a priori, and they train better the recurrent neural networks. HMMs are applied to diverse sequence recognition tasks. Applications of HMMs to bioinformatics is given in Boddy and Bruneck in 1998 and to natural language processing in Manning and Schultz in 1999. It is also applied to online handwritten character recognition, which differs from optical recognition in that the writer writes on a touch-sensitive pad and the input is a sequence of XY coordinates of the pen tip as it moves over the pad and is not a static image. Banjo et al. In 1995 explained a hybrid system for online recognition where an MLP recognizes individual characters and an HMM combines them to recognize words. Various applications of the HMM and several extensions, for example, discriminative HMMs, are discussed in Banjo 1999. The more recent study and survey of what HMMs can and cannot do is Biomes in 2006. In any such recognition system, one critical point is to decide how much to do things in parallel and what to leave to serial processing. In speech recognition, phonemes may be recognized by a parallel system that corresponds to assuming that all the phoneme sound is altered in one time step. The word is then recognized serially by combining the phonemes. In an alternative system, phonemes themselves may be designed as a sequence of simpler speech sounds if the same phoneme has many versions, for example, depending on the previous and the following phonemes. Doing things in parallel is good, but only to a degree. One should find the ideal balance of parallel and serial processing. To be able to call anyone at the touch of a button, we would need millions of buttons on our telephone. Instead, we have 10 buttons, and we press them in a sequence to dial the number. We will discuss graphical models in chapter 16, where we will see that HMMs can be considered a special class of graphical models, and inference and learning operations of HMMs and analogous to their counterparts in Bayesian networks. This is provided by Smith, Hagerman, and Jordan in 1997. As we will see shortly, there are various extensions to HMMs like factorial HMMs where at each time step there are a number of states that collectively generate the observation, and tree-structured HMMs where there is a hierarchy of states. The general formalism also allows us to treat continuous as well as discrete states known as linear dynamic systems. For some of these models, exact inference is not possible, and one needs to use approximation or sampling methods.